All right, so in the next part of the lecture, I'm going to start now talking about the lead compensation. So now, what is a lead compensator, and what is the difference between, or what are the differences between the lead compensator and the lag compensator? So in the design of a lag compensator, as we saw, we saw that a lag compensator can improve steady state error, while it can at the same time have a minimal effect on the phase diagram, so it would result in an imperceptible change in the transient response. So really, if you want a good improvement in steady state error, as well as an improvement in the phase margin, you can actually use a lag compensator. But now, in the design of a lead compensator, we really want to change the phase plot. So because we want to increase the phase margin in order to reduce the overshoot, and also we want to increase the bandwidth. So really in this case, the goal is to increase the phase margin, at the same time increase the bandwidth. So now they increase the bandwidth. If you remember before, increasing bandwidth means that you're actually going to have a faster convergence to your desired set point, and that means, for example, you're going to have a lower settling time, and often that also translates into lower peak time and rise time. So all right, so in this figure you see a visualization of the lead compensation. So in fact, the lead compensator, as you see, it increases the bandwidth. So you actually go from here to here. This is uncompensated, and this is the compensated system. So it increases the bandwidth by increasing the what is called gain crossover frequency. So really, the gain crossover frequency is where the first time the magnitude plot crosses the 0 dB line. So in this case, if this is 0 dB line. For uncompensated system, this is the crossover frequency. For compensated system, this is the crossover frequency. So if you increase the crossover frequency, that means that you're going to speed up the convergence, basically. So at the same time, the phase diagram is raised. So as you see, if you at high frequency specifically, and the result is a larger phase margin and a higher phase margin frequency. So, and of course, in the time domain, lower percentage of overshoot, which means larger phase margin with smaller peak time, or meaning higher phase margin frequency, are actually the outcomes. So now these are actually shown here. So now, as you see, the uncompensated system has a small phase margin. So if this is the uncompensated system, so if this is going to be the crossing the 0 dB line, this is going, okay, so now the difference between this line and negative 180, so this much is actually going to be your phase margin. But now as the crossover frequency increases, so you're actually going to now look at the phase corresponding to this point, this frequency, which is going to be here, and therefore your phase margin is actually going to be this much. So obviously your phase margin has increased. So yeah, so at the same time, as you see, just because your gain crossover frequency has increased from this point A to C, that means that it obviously results in a larger phase margin, as well as a larger band, as well as a larger bandwidth. So I mean, this is actually going to be like an advantage of well, not really advantage, but this is actually going to be a feature of, or the characteristics of a lead compensator. So and of course, it takes the name lead because for all the frequencies, the phase angle of a lead compensator is always going to be positive, whereas for a lag compensator, the phase angle is always going to be negative. So if you remember, for For a lag compensator, the magnitude plot would be actually something like this. 0, it drops. It would be for a lag compensator. And of course, kind of similar thing for magnitude. For magnitude of a lead compensator, it starts from 0 dB, goes up, and then becomes flat. Whereas for a lag compensator, it starts flat, then goes down, and then becomes flat. So bottom line, using a lead compensator, you can increase or you can improve the phase margin. You can improve or increase the phase margin frequency. You can increase the bandwidth, which means an increase in crossover frequency. So these are really the characteristics of a lead compensator, and these are the benefits that you can achieve with the use of a lead compensator. So now so if you remember, for a lag compensator, for a very simple first order lag compensator, we actually had a pole and a zero, but the pole would sit between the j omega axis and 0. But now for lead compensator, we're going to have the 0 sitting between the j omega axis and the pole. Okay, so really the 0 is closer to the j omega axis than the pole is. So now mathematically speaking, a lead compensator with a unity gain, so with a unity DC gain can be actually expressed as what you see here, GC of S 1 over beta. So, and again, this 1 over beta is here because that just can provide you with a unity gain compensator. Multiplied by S plus 1 over T divided by S plus 1 over beta T. So now really the only thing that you have to design is just T and beta, or just to find out where the location of the pole and the 0 of the lead compensator is, just like for the lag compensator. So now for different values of beta, turns out that if you just plot the Bode plot, and of course if you just normalize it and plot it in terms of not just omega but in terms of omega t, so that the only parameter that you have to deal with here is beta but not beta and t, then it's actually going to look like this. So now, as you see, the phase magnitude, the phase angle is going to have a peak, and the value of peak and where that peak happens. So as you see, both the location of the peak in terms of omega and also the magnitude of the peak is going to be, and by magnitude I mean the actual phase angle of that peak is going to be dependent on the value of beta. So now it turns out that if you just do some math, you can find where that peak is going to happen. It turns out that that peak is going to happen at the frequency of 1 over t square root of beta. And if you then just plug this frequency back into the expression for the phase angle, the maximum phase angle is just going to be the arc sine of 1 minus beta divided by 1 plus beta. For instance, here, if the value of beta is 0.1, it's just going to be, as you see, it's just going to be the phi max is going to be arc sine of 1 minus 0.1, which is 0.9, divided by 1.1. So really it's going to be 0.81, and arc sine of 0.81, and the arc sine of 0.81 is something like 55 degrees. It's somewhere here. Okay. And you can also determine that at that peak, well, at that frequency where the phase angle shows a peak, at that same frequency, the magnitude of GC of the compensator, the value of it is actually going to be 1 over square root of beta. And again remember, this is in degree, but this is not in dB. This is just in decimal. So now we're actually going to take some of these calculations and some of these equations and we're actually going to use this in order to help us with to come up with a design procedure I'm in the next lecture, I'm going to discuss this design procedure for lead compensation. I'm also going to give you a couple of examples. So these are going to come up in the next lecture.